everyone. I am Ember. Welcome, or welcome back. Recently, a viewer wrote me a long series of comments about how the Big Bang isn't science because it can't be observed. This viewer isn't alone in thinking that. Misinformation peddlers like Matt Powell assert that kind of thing every day, and it steers a lot of people wrong. So today I want to do something a little different. I want to show you how we came to the idea of the Big Bang, what science supports it, and how we can actually observe it even today. And, at risk of oversimplifying a bit, I want to do it in a way most people can understand. This is For Science! So the name Big Bang was coined by a scientist named Fred Hoyle. He was, to put it mildly, not a fan. He was a serious physicist. He was the guy who figured out how the elements, all the way up to iron, are made by fusion in the hearts of stars. That was a huge contribution to science. But he liked an alternative model of the universe called the steady-state model, which was, as you might expect, the concept that the universe doesn't really change. It is on the largest scales, pretty much the same, past, present, and future. But I'm getting ahead of myself. The first hints of the theory came with Einstein's special relativity. He wasn't the first to posit a relativity theory, but his was a game changer. Until then, we didn't know there was a speed of light. It gave us a basis for consistent laws of physics all across the universe, new rules for velocity and acceleration, and weirdest of all, the concept of time dilation. That last part is absolutely critical to what we're going to see at the end. For right now, though, think about it this way. The speed of time itself can be stretched or compressed. In special relativity, Einstein was only looking at it in terms of relative values. If you're stationary and I fly past you at half the speed of light, the flow of time itself will be different for each of us. For every 100 seconds that pass for you, I'll only get 85. That's a 15% difference in the speed of our relative streams of time. And that's because of how much closer to the speed of light I'm going from your point of view. But it gets weirder. The speed of light is constant for everyone, regardless of their frame of reference. To me, I can measure the speed of light and I'll get the same result as always. So if a spaceship passes me going at half of the speed of light I measure, I'll have 100 seconds to their 85. That was pretty cool knowledge, but didn't yet change the way we viewed the origin of the universe. That would come a few years later. Einstein published his general theory in 1916, but World War I got in the way of a lot of science. It wasn't until 1919 that Arthur Eddington managed to execute a test of the new theory. I should explain. Newton gave us a pretty decent set of physics equations, but they fell short in one obvious area, the orbit of Mercury. Newton could predict the orbital motions of every other major body in the solar system. Mercury is the closest of the planets, and it orbits fast, just 88 days. That part was no problem, but the thing is, the orbital path itself is also in a kind of orbit. We call the phenomenon precession. Gradually, Mercury's ellipse will make its own path all the way around the Sun, carrying the speedy little planet with it. Newton was absolutely stumped. The flaw in Newton's thinking was that he envisioned gravity as a force. Einstein reimagined the concept of gravity as a bending of space itself around massive objects. It sounded really weird, but the equations explained not only everything we already knew, but had an answer for the peculiar orbit of Mercury too. So, after hundreds of years, we finally had math that fit the universe we could see in our own backyard. But that's not enough to validate a theory. It has to match the real world, sure, but it also needs to make testable predictions. One of the easiest predictions to test, way back in the early 20th century, was the deflection of starlight by a big gravity area. That was another area Newton and Einstein differed. Newton said large masses would bend starlight a certain amount. Einstein said a much larger amount. I apologize for being vague there. but the amount of deflection depends on the apparent distance from the mass in question, and the math gets a little complicated. Suffice it to say, the two theories were way off from each other. The drawback was, the only mass handy that was big enough and close enough to create the effect necessary was the sun, which has an annoying tendency to render the nearby stars invisible by turning night into day and making the sky all blue and whatnot. Solution: a total solar eclipse. Only during such an event could we see, and more importantly measure, the stars behind the sun. But those don't happen every day. The next eclipse got derailed by World War I, and the one after that was 1919. So Arthur Eddington sailed to a remote island with the best photography equipment he could bring along. He put years into this expedition, got everything all set, and clouds. As an astrophotographer myself, I can appreciate the uniquely intense frustration of clouds getting in your way during an important celestial event. But all was not lost. During the moment of totality, the clouds thinned just enough to let the camera see a sliver of sky. And behold, stars. Eddington had to take the plates all the way back to the UK to develop. So for weeks he was en route, not even sure if he'd gotten what he'd come all that way for. The anxiety must have been driving him batty. But return he did, and the photos were developed, and lo, a science miracle! For one plate, a single exposure revealed the elusive stars. Measurements ensued, and Einstein prevailed. So, the new theory got its first solid confirmation, but so far, it amounts to just an upgrade in our math. Just a few years later, in 1923, astronomer Edwin Hubble shook the foundations of the cosmos. Up until then, we thought our galaxy, the Milky Way, was the only galaxy. It was the whole universe as far as we were concerned, and the universe ended at the edge. Stars gradually fading out to void. But in 1923, Hubble used a special star called the Cepheid variable to calculate the distance to the Andromeda Nebula and got an inconceivable result. It was 1,000,000 light-years away. For reference, our galaxy is about 100,000 light-years across. The gas cloud everyone had thought was just a nebula was farther away than the size of the whole universe at that time, 10 times over. He proved that many of the nebulae we could see in the sky were actually entire galaxies in their own right, so vastly distant we could not even fathom the idea until just then. Then, in 1929, he did it again. He'd been finding and measuring galaxies like the madman he was all this time, and he noticed something rather odd. Pretty much all the galaxies he could find had their spectra shifted redwards. I should explain. Every star emits a spectrum of light, and that's what generates the rainbow you see when you shine light through a prism. It's all many different wavelengths, but with stars, we can tell some important things about their composition from absorption lines, missing bits of their spectra where an element is absorbing that specific wavelength. These lines always show up at those specific wavelengths depending on the element. Hydrogen, for example, always looks like this. So when we see a spectrum like this, we can see those are definitely hydrogen lines, but they're in the wrong place. The whole spectrum was shifted to the red side. Why? Here's a thing you've probably noticed yourself. When a car is coming up the road, passes you, and continues away, the pitch of the sound it makes changes. When it's approaching, the pitch is higher, because the motion of the vehicle is affecting the wavelength your ears are detecting. When it's moving away, the pitch is lower for the same reason. It's making the same noise as always, but the frequency of that noise is changed by the velocity relative to your ear. That's called the Doppler effect. It's part of how modern radar works, and the exact same thing applies to light, because light also has a frequency. A shift toward blue is like a higher pitch. A higher frequency is measured because of the motion towards us. Red is a lower frequency because of motion away from us. So, a red shift can indicate recessional velocity. That is to say, the galaxies were all moving away and fast. But not only that, the farther away they were, the faster they seemed to be moving away from us in every direction. Nobody could make any sense of it. Well, almost nobody. Enter George Lemaitre. George was a Catholic priest who'd been working on how to reconcile Einstein's new theory with the Bible. According to the theory, the universe, no matter how large it is, should be collapsing under its own gravity. It should crunch right up. Einstein had no good answer, so he added a term to his equations for an unknown force that kept the universe from imploding. He hated it, but he knew it must exist because, behold, the universe was still here. Lemaitre had another idea. What if, instead of imploding, the universe was exploding? Gravity perhaps had yet to catch up with and reverse the inertia of that moment of creation, as the church might put it. Factor in that Hubble had just shown all these newly discovered galaxies were all hurtling away in every direction as if a galactic firework had gone off. And we had ourselves a hypothesis. So that's where the idea of the Big Bang came from. A curious mix of new math, a new vision on the universe, and a religious researcher trying to motivated thinking the creation described by Genesis into being. We'd eventually come to understand it wasn't an explosion in the conventional sense, but a singularity. You may have heard that term used to describe the heart of a black hole, the place where time stops running and all matter loses cohesion. This singularity is like that in some respects, but it wasn't just ultra-dense matter and stopped time, but all of space as well. It wasn't matter exploding outward, but the space containing the matter expanding. There's a whole sub-theory dealing with that, and it's outside the scope of this video, but this whole concept of an expanding universe grew out of one Catholic's idea that maybe he could show Genesis might have been possible, if only in a metaphoric way. Believe it or not, quite a lot of our best science has come from very devout Christians trying to prove something from the Bible, and every time they wind up proving something else entirely. They don't want to, they resist it like mad, and they get a lot of flack for it, from being shunned to burned at the stake. But the truth is undeniable. But like we just said, it takes more than merely matching the world we see to verify a hypothesis. A lot of people didn't like the idea of a young universe with an explosive start, and the truth of the idea was far from a foregone conclusion. There were a bunch of alternative models put forth. One of the most robust was steady state, the idea of an infinitely old universe with no beginning at all. It simply always existed. That model had a hard time explaining the galaxies all racing away, but there was plenty of room for something else to be discovered that might explain that observation. One problem both models had was figuring out how the elements we see in the universe today came to be in the amounts that we see. That's where Fred Hoyle came in. Though he favored steady state, he worked out how the all-hydrogen universe used stellar fusion to create heavier elements like carbon, oxygen, all the way up to iron. And later, he again showed that all the rest of the really heavy stuff formed in the mega furnaces of supernovas, which also were handy in spreading all that fresh matter around the galaxy. Ironically, Hoyle's work tended to favor the Big Bang model, While the stellar fusion explanation worked for both models, Big Bang had an edge. If the universe were infinitely old, at some point in the infinitely distant past, all the hydrogen would have been cooked into bigger elements. That there was still so much hydrogen, but still plenty of other elements, was a strong indicator that the universe was relatively young. Of course, Team Hoyle felt that there might have been some mechanism as yet unknown that was adding new hydrogen to the universe. It wasn't impossible, but that was 2 for 2 on observations that depended on an as yet unknown mechanism to fit the model to the real universe. It was starting to look a lot like Ptolemy's old solar system, with epicycles upon epicycles needed to make the observations fit the preconceived ideal. So, Big Bang had an explanation for the observed galaxies flying apart, and an explanation for the abundance of hydrogen, yet plenty of other matter, all with no extra steps necessary. It was heavily favored by razor owners named Occam. But what was really needed was a test, a prediction, like Einstein's bent starlight. It turns out we had one of those. In 1948, George Gamow and company, who were working on the chemistry of the early universe, predicted that at a certain point, the whole universe would suddenly become transparent to light. Like the space we see today, light passes through no problem. The early universe was a hot, dense soup, and light couldn't go very far without hitting another particle of matter. It was a photon ping-pong. But at some point, like opening a curtain, the light would shoot out freely across the whole universe. If the ongoing expansion of the universe was real, if that was the cause of the fleeing distant galaxies, then that first light should be even more redshifted than the most distant galaxy. Far, far more redshifted. In fact, it would be so vastly shifted that it wouldn't even register as visible light anymore. It would be all the way over in the microwave band. It took a hot minute, but in 1964, a couple of scientists from Bell Labs named Penzias and Wilson discovered a weird static in the microwave band. It seemed to be coming from everywhere, which is really weird. Everything from light to radio to gamma rays all radiate from a point source. But this signal, this one signal in all the universe, was coming from every direction at once. It was the cosmic microwave background radiation, an ancient light beyond all concepts of ancient, that came from every point in the universe, all at once. It took us years to build a device to measure such an unusual signal, and we had to get that device up into space to get it away from the interference from the Earth and its technological civilizations. But in 1989, we got that satellite, the Cosmic Background Explorer. We've since followed it up with other satellites with better instruments and collected even more data. But the bottom line is, we found the echo of that first light, still shining all these years later. It's still shining today. You can Google CMB and see lots of images published by NASA, the ESA, and many of the top names in astrophysics on the planet. You can see it for yourself in those images. Or, if you want to buy a specialized detector, you can repeat Penzias and Wilson's discovery by pointing that sensor anywhere in the sky. It's science right there for you to see and confirm for yourself. It's the only omnidirectional source we've ever found. But that's not all. This is 3C273, and it is a spectacular phenomenon called a quasar. These monsters are incredibly far away, but shine more brightly than entire galaxies. This was the first one identified in 1963, but we've since cataloged dozens upon dozens upon dozens. The neat thing about these is that they are all vastly, vastly far away. Knowing what we know about the speed of light, that means they are also vastly, vastly far back in time. The light from a galaxy 1,000,000 light years away, like Andromeda, takes 1,000,000 years to reach us. So what we're seeing today is light from 1,000,000 years ago. Now apply that to a galaxy 5,000,000,000 light years away. That's light from 5,000,000,000 years ago. And most quasars are several billion light years away, which means they were blazing several billion years ago. 3C 273 is an outlier, very close, very recent, and even that is perhaps 1,000,000,000 years back in time. That's so long ago, life was just starting to form multicellular organisms. That's so long ago, the sky was just starting to turn from orange to the blue we see today. The fact that these brilliant lights only existed billions of years ago, with none of them to be found in the present era, shows that the cosmos is evolving. It was different in the past than it is today. That's another sign that the universe isn't static, and has a definite beginning. And remember back in the first part of this video, I asked you to keep in mind that time-stretching effect? Remember, the Big Bang is a mathematical consequence of general relativity. Relativity requires that as objects near the speed of light as we perceive it, the rate of time they experience as we perceive it slows way down. This is important because despite all the discoveries we've covered so far, there is still a chance that the universe might be eternal and static, just with a few unidentified phenomena and some weird local anomalies. It's asking a lot, but it isn't impossible. But one of the things that needs to be explained is the redshift of the distant galaxies, that mark in their spectra that shows they're all flying away at rates directly pegged to their distance. It could be that they aren't moving at all, and something else is to blame for the redshift in their light. But good news. There's a test we can do to tell the difference. If they are holding still, relatively speaking, then the flow of time there should be about the same as it is here. But if they're moving at nearly the speed of light from our perspective, like some of the most distant galaxies seem to be, then the time we observe from them should be dramatically dilated compared to our own local flow of time. That's what relativity predicts, and therefore that's what the Big Bang predicts. And as it turns out, there are a few things we can check to see which is the case in the real universe. One of our favorites is called Type 1a supernova. We like those for two reasons. First, they're incredibly bright, and so much easier to see at these extreme distances. Second, they always happen in a certain way. They get bright fast and then dim at a known rate. So, when we look at a Type 1a supernova in one of the most distant galaxies, what will we see? Will it take as much time as it does here to execute its brightness curve? Or will it take much longer because the high recessional velocity is slowing the relative rate of time's passing? As it turns out, you can probably guess, considering the video you're watching, yes, distant galaxies show a time dilation, proving the prediction and demonstrating they are in fact moving at the incredible speeds that they seem to be. So there you have it. There are veritable truckloads more evidence all backing this model, and I encourage you to look into it. The mysteries of the cosmos are intensely fascinating, filled with wonderful sights and strangeness beyond imagination. But for our purposes, we have proof and then some that the Big Bang is probably true. That doesn't mean it won't be replaced by another model someday, just like Einstein's math replaced Newton's because it did a better job of explaining the real universe. That said, it's passed test after test after test after test. Some of the biggest pieces of evidence you can go out and confirm for yourself. So, to respond to those comments I mentioned at the start, and the skewed thinking they demonstrate in the minds of millions of people more. It's true we can't witness the singularity at the dawn of time directly, but there is a veritable mountain of measurable evidence that it happened that can't be explained any other way. And we can still observe both its first light and its lasting effects today. The expanding universe of general relativity isn't some long ago event, but an ongoing process that shapes the universe we live in even now. Thank you for taking this journey across this piece of the cosmos with me. If you enjoyed this video, please take a moment to like, share, subscribe, comment, any other buttons you can find, because every interaction helps make this video more visible to more people. Thank you. Videos like this take considerably longer to produce, so if you'd like to see more in-depth content like this on this channel, please consider adding your support over on Patreon. One of the chief differences between science and religion is that science tells us not just what we know, but how we know it, so any person can go back and check on any fact at any time. That's just one of the reasons why we are better than religion.